Today we are going to prove Rolle's theorem. Rolle's theorem was first published in 1691 by the French mathematician Michel Rolle. He was a vocal critic of the methods of his day and attacked calculus as being a collection of ingenious fallacies. Later, however, he became convinced of the essential correctness of the methods of calculus. What is Rolle's theorem? Let f be a function that satisfies the following three hypotheses. Function f is continuous on the closed interval from a to b. Function f is differentiable on the open interval from a to b. Function of a is equal to function of b. Then there is a number c in the open interval from a to b such that the derivative of function of c is equal to 0. When using cases in a proof, the main rule is that the cases must be chosen so that they exhaust all possibilities for an object A in the hypothesis of the original proposition. Following are some common uses of cases in proofs.
Alright, today we're going to be proving Rolle's theorem. So we'll start off just by showing it once again. If f of x is continuous on the closed interval a to b, and f of x is differentiable on the open interval a to b, and f of a is equal to f of b, then there exists at least one number, c, in a to b such that f prime of c is equal to 0. That is Rolle's theorem, and all it's saying is that somewhere along a function between two equal value points, there is a tangent line that is horizontal. And we're going to prove that by showing three cases. First case being where f of x is equal to f of a and f of b. The case where f of x has some point greater than f of a, and the third case is where f of x has some point less than f of a. So for the first case, we're going to take, if f of x is equal to f of a for all x in the interval a to b, then f of x is constant, meaning that the graph is constant, and the graph is a horizontal line. As a result, the derivative of that, f prime of c, is equal to 0 for all values of c in a to b. So basically all we're saying is that if we have this interval a to b once again, and f of x is equal to f of a, all that's saying is that our function looks like this. Let me use a different color. It's hardly a different color, but our function is just a straight line across a to b, meaning that f of x is equal to f of b. And we know that f prime of c, and then we can take any point to be c, and we know that f prime of c is equal to 0 due to the fact that the derivative of 0 is 0. Alright, case 2, we're going to look at when the function f of x is greater than f of a for some x on the closed and bounded interval a to b. Since f of x is continuous on a to b, we can apply the extreme value theorem. The extreme value theorem states that if a real valued function f is continuous on the closed and bounded interval a to b, then f must attain at least one maximum and one minimum. And that tells us that f of x has some maximum at x equals c in the interval a to b. And since f of c is a maximum, we know that the tangent line is going to be horizontal, which means f prime of c is equal to 0. So to make it in more simple terms, if we have, once again, our function from a to b, we have f of x, and at some point it's higher than f of a, so we'll say it looks like this. It could also just be one large hill. Doesn't make too much of a difference. What this is saying is that there's some c where, or the extreme value tells us that there's some c where we achieve a maximum and a minimum. So we'll take our c to be the maximum, but we could also take it to be the minimum, which is actually going to be case 3. So we take c to be this point, which is our maximum, and the extreme value theorem tells us that it is in fact a maximum. And that means that we know that there's a tangent line here. And by the extreme value theorem, we can say that f prime of c is equal to 0 here. For case 3, it's almost identical to case 2, except instead of f of x being greater than f of a, we're going to say f of x is less than f of a. This is the final case that we have to cover to prove Rolle's theorem. So while f of x is less than f of a for some x on the interval a to b once again, we can again apply the extreme value theorem to confirm that f of x has a minimum for some x equals c in a to b. It's the exact same process, so I won't go over it again, just case 2 all over again, except it's going to be underneath the graph instead of above it this time. And we know that since f of c is a minimum, f prime of c is equal to 0. So once again, I'll just draw a real quick graph of this function to show. Now all we're saying is that some point on f of x has to be underneath f of a. So it could look something like this. It could also go underneath and then above. It doesn't make too much of a difference. But all we know is that at some point, thanks to the extreme value theorem, at some point c, there's going to be a minimum, and that minimum will have a tangent line whose slope is 0, which is what we're trying to prove. So now that we've shown all three cases, that proves that Rolle's theorem does in fact hold true.